In this review, we're going to cover some key components of multivariable calculus that'll help us in our 2 semesters of PChem. So we'll go over partial derivatives and multiple integrals and spherical coordinates. So in physical chemistry, we are a lot of times interested in real systems. And real systems, whether it be an atom or a piston full of gas, have 3 dimensions. So we often need to do things like take derivatives of functions that depend on multiple variables or integrate over 3 dimensions. So first we'll start off with partial derivatives. If you're not familiar with partial derivatives, they are very simple. So a partial derivative is just a derivative with only one variable. So these come into play with multivariable functions. So say we have a function that's a function of 2 variables, x and y, and this function is equal to x squared y cubed. Well, how do we take the derivative of this function? And so we can either take the derivative of this function with respect to either one of its variables, with respect to x or respect to y. And when we do that, just like we would do a normal derivative, so if we were taking the derivative with respect to x of 8x squared, we just ignore the 8, it's a constant. And this is going to be 16x. So in the same way, when we take the partial derivative of this x squared y cubed with respect to x, we just treat y like it's a constant because it's not changing with respect to x. And there's a notation change when we do partial derivatives. We use this del instead of a d, but we take the partial derivative with respect to x of our x squared y cubed, and this is simply 2xy cubed. We can also take a partial derivative of this function with respect to y, so x squared y cubed, and that gives us 3x squared y squared. So all of the rules we know from taking derivatives are the same, and we simply we just treat all the one variable as a constant, and it's not the one we're taking the derivative with respect to. And the reason that we're going to be doing this, and we'll see this more next semester, is if we're looking at multivariable functions. So say we have a function, we have an x direction and a y direction, and we have some shape that this function is making, and we want to know, well, I'm starting here and I'm, ending up here. What's the change? And we assess the change, this derivative with both x and y, as if it's the sum of the derivative with respect to x, so how x is changing, and then the derivative with respect to y, and we can sum those up and get a good estimation for the total change. And we'll see this more next semester. And what we'll end up seeing a lot this semester is multiple integrals. So again, just like we've seen for partial derivatives, sometimes in physical chemistry we need multiple dimensions. So in calculus, we would do things like integrating over a space. So for example, we could integrate, we could have a function that looks like this, and we would integrate this function and find the area under the curve, and that would be our answer. But in some cases, in physical chemistry, we're going to take a hydrogen atom, and we want to know where's the electron going to be. And to do that, we don't just have a one-dimensional problem, but we have a three-dimensional problem because this electron can be, in any direction around the central proton of a hydrogen atom. So how do we go about evaluating this? So let's start with a simple example, and then we'll move on to doing a sphere, which is more commonly what we're going to see in physical chemistry. But let's say we want to integrate a function. So we have a function that is a multivariable function of x, y, and z, and that function is 10x squared y z to the fourth. So if we want to integrate this function over a 1 by 1 by 1 cube, so say we want to have our x, y, and z in between 0 and 1, we would just do the same thing that we would do for a regular integral. So we take 3 integrals, and they're all between 0 and 1 of our function, so 10x squared y z to the fourth dx dy dz. And for clarity, we can rewrite this. So each one of these integrals has to do with a different variable. And for our purposes in physical chemistry, where all of the functions we're going to be taking multiple integrals of can be completely separated. Here we have a function that's dependent on x, one that's dependent on y, one that's dependent on z, and they're not interrelated in any way. That's going to be our assumption, and we'll see that throughout the semester. So we can split this up into one integral that's just for x. I'll put the 10 outside here. So we have 10 times the integral of x squared dx from 0 to 1, and then y dy from 0 to 1, and then z to the fourth dz from 0 to 1. And then you would just solve this integral like you would three separate integrals and multiply the answers together. So this is going to equal 10 times the integral of x squared is, of course, 1/3 x cubed, evaluated from 0 to 1. And then we have 1/2 y squared, evaluated from 0 to 1. And then 1/5 z to the fifth, evaluated from 0 to 1. So the plugging the 1 into all these variables is going to make them 1, and then the 0 is going to make them 0. So at the end of the day, our answer we'll find is 1/3. So this is great and works for our Cartesian coordinates, but in most cases in physical chemistry, so we'll do some particle in a box, but a lot of the time we're going to end up in spherical coordinates because we're interested in this hydrogen atom example above. So, and if you've ever tried to integrate a circle in Cartesian coordinates, you know it's not easy. So we have a conversion that we can do to get to polar coordinates. So just a little review here. So we have our good old fashioned Cartesian coordinates. So we have our x and y, and then we have a z-axis. So we have three dimensions. We can have a point on this, and we can look at its axis. So it can be, this can be its x value, and then this can be its, we'll do a z value here, but maybe it lies off the beaten path here. And so we have a y value as well for this point. All right, so we have three dimensions that this point is occupying. We have an x, y, and z. And we can describe it perfectly with Cartesian coordinates. However, it turns out to be much easier to do integrals over things like spheres if we use spherical coordinates. So we can describe the same point here, and we still have our three Cartesian dimensions here, so we have the same point. But rather than describing it with x, y, and z, we're going to describe it with r, theta, and phi. So it has some distance from the origin, and we'll give that r. And then it has some angles based on two different points of view here. So it has an angle here, theta, that goes from the positive z-axis to the negative z-axis. So the maximum theta goes from 0 to pi. And then it also has some angle phi that goes all around the xy plane. So we have a maximum, so phi goes from 0 to 2 pi. So this is our spherical coordinates. And I'll write out what I just said here. So we have r, which is in between 0 and infinity. It doesn't make sense to have a negative radius. And we have theta that goes between 0 and pi. And we have phi that goes between 0 and 2 pi. And with any set of these three variables, we can describe all of the same points we could describe with our Cartesian coordinates, x, y, and z. And I want to just note, if any of you have taken advanced math, sometimes in the chemistry textbooks, we'll switch theta and phi compared to math textbooks. So just be prepared and make sure you know which variable we're talking about. So if we want to describe spherical coordinates and integrate over spherical coordinates, we have to make an adaptation from our good old-fashioned dx, dy, dz that we would do for Cartesian coordinates. And when this converts into spherical coordinates, it does not just convert into dr, d theta, d phi. So what it actually converts into is r squared sine theta dr, d theta, d phi. And the details of this aren't super duper important, but it accounts for how you convert to taking an element that's cube based in the Cartesian coordinates to one that's spherical based in the spherical coordinates. And the back of the textbook will go into this if you're interested. but just be sure that you're using r squared sine theta when you're doing spherical coordinates. And what we'll often end up seeing is that we're trying to find, what probability is an electron, being, say, 10 nanometers away from the nucleus, or 5 angstroms, or something. And we don't really care about the angle. So if we don't care about the angle, we're going to be integrating over all of our angles up here, and that will simplify our spherical coordinates. And now, again, this is not going to be in the case for every problem you'll do, but for many problems you'll do, that'll be the case. So if that is the case, we can take our general integral. So we have our triple integral of some function of r, theta, and phi. And now remember, we have to have r squared sine theta, dr, d theta, d phi. And just like I said before, in many cases, our function, it will actually only be a function of r. And then we don't care about the angles. So this will simplify into an integral from 0 to 2 pi, just based on phi, because there's no phi element in here. And then we have an integral from 0 to pi, that is sine theta d theta. And then we'll have some integral of our function of r, whatever our r is, times r squared dr. And this could be, we could be trying to find, it could be 0 to infinity, just over all of space, or maybe we're trying to find something, so maybe it's like, what's the chance of finding it between 10 angstroms and 12 angstroms, or something like that. And I will encourage you to do these integrals on your own, but what you'll see is if you can evaluate these integrals here, and this one ends up being 2 pi, and this integral ends up being 2. So this whole thing will simplify into 4 pi times the integral of our function of r squared dr. So this result is something you might see in the textbook, or you might encounter, like, how the heck did we get that 4 pi? Well, this is how. All right, so with this, hopefully you are prepared enough to do the simple multivariable calculus problems that we need to do to evaluate important physical chemistry problems.